Right, we're going to do more differential equations. So we're going to have a look at forming them and then solving them in this lesson. So some of this is actually linked to at the end of the differentiation chapter, where there was some stuff related to rates, and we're going to pick up on that now. So we need to turn some worded statements into equations and then use those to solve. So the rate of increase. Well, this is pointing towards time, isn't it, of a rabbit population. So we're going to go ahead and say the change in population as time changes is proportional. So let's introduce this one again. Is proportional to the current population. So if if population is really big, this is a really big number. That's what this means. Form an equation. So this is a statement, but we want to make it an equation. You might remember from GCSE that the way we do that, if you change this to an equal sign, you can do that, but there's some sort of constant that ties them together. So we can put K in here. Okay. That means that if you do this, multiply that by some number, you should get this. Okay. So that's our equation. Okay. Form a differential equation. Well, this is a differential equation, and find its general solution. Why is it a differential equation? Because it's got P, and then it's got its derivative in the same equation. Now, I know there's no T there at the moment, but this is still a differential equation. So if we want to solve it, we need to follow those steps from before. So the first part we talked about was separating. So dt needs to be moved up, and p needs to be moved to the left to go with p. Now the k could actually, you could move that down with the p, or you could leave it. I'm going to leave it there because that's typically what is done in questions. If there's a number here, whether it's 2 or 3 or k, that tends to get left there. So let's take a look. We get this one here, and then we bring the dt up. So we get 1 over p equals k dt. And now when you integrate on both sides, that's when t might actually appear. So natural log of p plus kt. So why does that happen? Well, imagine if I asked you to integrate the number 2 with respect to x. The answer is 2x, isn't it? Because 2x differentiates to this. It's the same sort of idea. So k with respect to t must be kt, because that would differentiate to just k. Okay, so kt, and then there's that c again, and we tend to put that on the right hand side. There's only one log involved here, so we can just go down this road, do e on both sides. All of that is in the power, and then we said ec times, not plus, times ekt is the same thing. Okay, and they've used the letter a instead to come up with this final answer. Okay, and there we go. We're solved because we have an equation for population, and derivative is not in there. So notice that it's also an exponential. So you often end up with exponential equations at the end of questions like this, but not always. Let's try a more difficult one. So water in a manufacturing plant is held in a large cylindrical tank of diameter 20 meters. Water flows out the bottom of the tank through a tap at a rate proportional to the cube root of the volume. Right, show dH/dt. So there's a lot of information here. We need to just be a little bit careful. A tap. Let's talk about this tap first. So water flows out. So what is water flowing out? That's volume. It flows out at a rate, and it's proportional to the cube root, right? The cube root of the volume. So you have to be able to turn this whole statement into this statement, okay? And then we also said that we know you can make it an equation if you introduce k, I'm not going to introduce k though, because look, this is dv dt, dh dt, and they've already got k, so I don't want to use the same letter because that's confusing. I'm going to use what's not used, m. Okay, m cube root v. So that's dv dt, and here they have dh dt. So if you cast your mind back, what do you think might happen here? Well, this is one of those related rate questions. So dh dt, I need to show what that's equal to, and it seems to me that using dv dt is heavily suggested. So I've got that piece already. What would the other piece have to be? dv's, so that disappears, dh. So I need dh dv as well. Well, is there anything that links height and volume together? Yes, there is. It's a cylinder. So a large cylindrical tank. So what we can do is we could say, well, the volume equals pi r squared times height. Okay. And in fact, r is 10, isn't it, in this case? So v equals, let's say, 100 pi h. And then if you differentiate, you get dv over dh equals 100 pi. That's dh over dv. Okay, so turn it upside down. dh over dv is 1 over 100 pi. So I'm going to multiply that one there by that one there. Let's have a look at their solution. Okay, so I've got this one here. So actually we have h here, and we still have v. So we'd still have a problem here, wouldn't we? We'd still have a problem. But volume is equal to 100 pi h. So underneath that one there, we could replace that with 100 pi h. Yeah. So you're thinking it looks a little bit different. That's why it looks a little bit different. Okay. We multiply them together. So there are only h's. So I should have looked ahead a bit, really, because there's no v there. So we multiply them together like this. And root h. And I suppose you could break all of that up into minus, they're using c, I'm using m, minus m root 100 pi over 100 pi times root h, using surd rules. Okay, using surd rules, you could break that bit up there, and that now matches what they've got there. Okay, so that's quite an involved question. That's like related rates. So if you're not sure about that, go back to chapter 9, differentiation. That's where we talked about that. Okay, now the reason why this is to show that question is so that if you can't do A, and A is a hard question, so that if you can't do A, you can still do B. So what I'm going to do is I'm going to clear the whiteboard, and then we're going to answer part B. Okay. So show that the general solution of this differential equation can be written in this form. So you might say, well, don't I have to use that minus, what was it, m cubed 100 root 100 pi? No, you don't have to use that. You can keep it as an unknown here, and what will probably happen later on in the question is we will put in some numbers that we know and then find that number, but you don't have to keep using this unknown. So in the same way that c could have just been written as natural log of k, and you didn't need to worry about it too much, you don't need to worry about that result for that k that you just found. Let's move on to the next bit. So it can be written in this form, h equals, but at the moment it's dh dt. So this suggests we should do what? Well, let's work through our steps. First of all, let's separate. So I think I'm going to rewrite this as, what's the easiest way to do this? So I could put this as h to the half, and then when I put it on the other side, it's going to be h to the minus a half, isn't it? dh. Move the dt up here, and I think I will just leave the minus k there. Oh, sorry, that's the cube root. That's the cube root there. So that should be minus a third. That's why you have to check over your work, things like this. So h to the minus a third dh equals minus k dt. So that's the separating step. So all the h's are on one side, all the t's are on one side. Again, you might say, where's the t? Well, it's the t is to the power of 0. You can't see it. How do I know that this is a good idea? Well, I also see t here. It implies that it's sort of just to the power of 1. So I feel like this might be the right way to go. After this one here, well, we can integrate on both sides. Okay, so if we integrate on both sides, we're going to have what? We're going to have h to the 2/3, because minus a third plus 1 is 2/3. And then you multiply by the reciprocal of the new power, which is 3/2, is equal to minus kt plus c. Okay. Does that look a bit like this? Well, it has a 3/2 in it, which is hopefully not a bad sign, but it's not really obvious yet. One thing to notice, P minus QT is quite similar to this part here, isn't it? If you change the order, that's like C minus KT. So that's not too bad. 3/2. So you can undo this by multiplying by 2/3 on both sides. That will undo that. So that will give you h to the power of 2/3 is equal to 2/3. I'm going to multiply it out because I want it to try and look like this as much as possible. 2/3 c minus 2/3 or 2k thirds, whatever, something like this, t. And can you see I'm almost there? Because p and q are supposed to just be numbers. Well, c is just some number and k is just some number as well. So that works. To the power of 2/3, the best way to undo that is to do to the power of 3/2, because then this will all cancel out. So what did I do to the power of 3/2? And there you go. We've got that result there. Okay, so working through the steps, separating the variables, looking ahead for some clues. It's not that obvious, this one, because a lot of stuff is hidden inside of P and Q, how it's written, but that's what we're going for. So again, I didn't have to mess around with K. Imagine if I left K, the number that it was from part A, that would have made this super complicated. So it's much better to just use that one there. And there we go. And in fact, when we use this one now, we're going to use this form here. We don't need to keep going back to minus 2/3 k. That's just some number. We can find out that number when we put some numbers in later. So initially, the height of the water, so h is 0. That's saying to me, isn't it? Oh no, that's saying t is 0 when h is 27. That seems like that might be important. 10 minutes later, so when t equals 10, h equals 8. Look at what we've just done. We've got this result here. Even if we couldn't do A and B, what do you think we should be doing? That's right. We should be substituting those numbers in there, and it will let us solve P and Q. If you put the first one in, an answer of 9 will pretty much just jump out straight away. And then you do the next one, you already put 9 in, and you should get an answer for Q. What that means is that the height is equal to, let's put these numbers in, 9 minus a half t to the 3/2. So now we can remove the mystery surrounding what those numbers were. This is the time to do it. And the final question is find the time when the depth is 1 meter. In other words, if this is 1, what's that t value there? So we can solve by doing some inverse operations. So that would be worth quite a lot of marks. That would take you a bit of time, that a question like that. But notice, even if your mind goes blank for A, you should pick up from B. And even if your mind goes blank for B, you should pick up from C. So everybody should be getting at least some marks there. Yeah, this is simultaneous equations. Pause the video then and have a go at this one here. So read the question really, really, really carefully. and have a good go before you unpause. Okay, so for part A, dV/dt is the rate of increase of volume with respect to time. Okay, why does it look like this? Well, there's some water, I believe, in this one pouring in. So that's pouring into the container, whereas the proportional blah, 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 this bit here is out. So how does the overall volume of the tank change over time? Well, it's 20 is going in, but then there is some amount going out. So this here takes into account the in and the out. So this is the overall change in volume over time. So a lot of information just to find that part there. For part B, solve the differential equation. And just before you do that, the container is initially empty. That might be quite a valuable thing to know later. T equals 0, V equals 0. That sounds like a boundary condition that you're going to use. Okay, so we integrate this one here. And the K, I don't know if we use this one yet. So C becomes minus 1 over K log 20. So the K we don't know about yet, but we get an equation in this form where A is 20 over K and B is minus 20 over K. We then get some more information. So that the rate of change is 10 when t equals 5. And what this will actually let you do is this will allow you eventually to work out what k is. So a little bit trickier there, that part C. So these are the kind of questions that you need to spend a fair bit of time practicing. And then that takes you to the end of Pure. So that is arguably the most difficult part of the most difficult chapter. So if it seems difficult, yeah, you're not alone with that. What I would say is you need to spend plenty of time on that now. And also remember that we're expected to be able to handle all of these different sort of variations of integration. And that's what makes integration so challenging. So best of luck to you. Make sure you do plenty of practice on that section there.